All right, welcome to the Explainer. Today, we're putting on our detective hats and diving into some serious chemical investigation. We've got an unlabeled vial, a total mystery, and we're going to crack the case using the science of deduction. Let's get into it. So, here's our case. This single vial, no label, containing some pure unknown ionic compound. I mean, it could be one of thousands of different chemicals, and our job? To figure out exactly what it is using nothing but the tools of chemistry.
And this is where the real fun begins. We're going to run a series of tests, and every single thing that happens, every bubble, every color change, any solid that suddenly appears, that's a clue. We just have to follow this trail of evidence, piece the puzzle together, and solve the case.
Okay, so every ionic compound has two parts, right? You've got a positively charged ion, the cation, and a negatively charged one, the anion, and they're stuck together by electric attraction. We're going to start our hunt with the anion. Gotta identify one half of our chemical culprit first.
First up in our lineup is the test for a carbonate, and it's actually a pretty simple reaction. We take a little bit of our mystery stuff and add some dilute acid. Now, if we see fizzing, those bubbles are our first major clue. That gas could be carbon dioxide, which is like the calling card of a carbonate. But we have to be absolutely sure.
So, to confirm it, we take that gas and bubble it through something called lime water. And here's the clincher. If that clear lime water turns all milky and cloudy, boom, that's the smoking gun. The cloudiness is actually a new solid, calcium carbonate, and it proves the gas was carbon dioxide. Which means, case closed on this clue. Our unknown has a carbonate ion.
But what if it's not a carbonate? Well, we move on to our next set of suspects, the halide family. For this, we add a little dilute nitric acid, then some silver nitrate. And as you can see, each halide leaves behind its own unique calling card. When the silver ions find a halide, they form this insoluble solid, a precipitate. If it's white, we've got chloride. A cream color points to bromide, and a really distinct yellow tells us we found iodide.
Okay, now the test for a nitrate. This one's a little more involved. You could think of it like a real multi-step interrogation. First, we add sodium hydroxide, then toss in some aluminum powder. We gently heat the whole mix up, and if a gas starts coming off, we test it with a piece of damp red litmus paper held right over the test tube. And this is our aha moment. If that red litmus paper turns blue, it means ammonia gas was created. What happened was the aluminum reacted with the nitrate in that alkaline solution and turned it into ammonia. This whole chemical chain reaction leads us straight to our culprit, a nitrate ion.
So, let's say we've positively identified our anion. Awesome! But the case is only half solved. Now we have to find its partner in crime, the positive ion, the cation.
For the cation part of the investigation, we've got two main techniques in our forensic toolkit. We can either force them to reveal themselves by creating those solid precipitates we saw earlier, or we can make them fess up their identity in a flame test.
Now, using precipitates can get a little tricky. When we add a little sodium hydroxide, a few different cations form a white precipitate. The problem is, 3 of our usual suspects, aluminum, calcium, and zinc, all do this. At first glance, they look exactly the same, so we need a clever way to tell them apart.
The trick is to see how they react when we apply a little more pressure, so we add excess sodium hydroxide. If that white solid just stubbornly stays there, we've found our guy. It's calcium. But if it dissolves and the solution goes clear again, our suspect is either aluminum or zinc. We've just narrowed the field. To finally distinguish between our last two suspects, we switch our chemical agent to aqueous ammonia. Now, if we added in excess and that white precipitate dissolves, we've unmasked zinc. If it stays put and refuses to dissolve, then our culprit is aluminum. It's a perfect process of elimination. Our other main technique is the flame test, which is basically a chemical fingerprint. When we heat up a sample, the metal ions get super energized. As they calm back down, they release that energy as light, and it's always a very specific color. A brilliant yellow flame just screams sodium. A delicate pale purple or lilac points to potassium. And a cool blue-green flame, that's the unmistakable signature of copper. You know, sometimes our chemical interrogations produce a gas. Now, these gases aren't just some random byproduct. They're actually crucial witnesses. Each one has its own unique property, its own testimony, that can help us figure out exactly what's going on in the reaction. Let's bring in our first gaseous witness, hydrogen.
If we think our reaction might be making hydrogen, there's a really simple and kind of famous test to confirm it. We just take a burning splint
And place it right at the mouth of the test tube. If you hear that classic squeaky pop, well, it's an open and shut case. That sound is a tiny little explosion of hydrogen reacting with oxygen, and it's the unmistakable confession of hydrogen gas. There's nothing else like it.
Next up in the witness box, sulfur dioxide. This gas can show up when we're testing for certain ions that contain sulfur. To identify it, we need a special chemical indicator, a solution of aqueous potassium manganate 7. And here is the key piece of evidence. That vibrant purple solution is a really strong oxidizing agent. When sulfur dioxide gas bubbles through it, the purple manganate ion is reduced and it becomes completely colorless. This really dramatic color change is the definitive positive test.
And of course, there are other key witnesses we need to know. We already met ammonia, the alkaline gas that turns damp red litmus blue. Then there's chlorine, a powerful bleach that turns damp litmus paper completely white. And oxygen has a really cool trick. It can relight a glowing splint. Each test is another specific tool in our detective kit.
So, we've gathered all this evidence. We've interrogated anions, cations, and even heard testimony from gaseous witnesses. Now it's time to go back to the detective's desk, lay it all out, and put the pieces together to finally solve this case.
And here's probably the most important lesson in chemical detective work. A single test rarely solves the whole mystery. A white precipitate is just a lead. A few bubbles are just a hint. But when you combine the results from an anion test with the results from a cation test, the clues start to support each other. They build a complete, undeniable picture of the compound's identity.
And really, that's the power of analytical chemistry. We start with a vial that could contain almost anything, but through systematic, logical detective work, we eliminate every other suspect, cross-reference our evidence, until we're left with just one, the confirmed positive ID of our mystery compound. But you know, this isn't just about a lab exercise. This exact process is the foundation of so much real-world science. It's how scientists test water for pollutants, how geologists identify minerals, and how forensic teams solve actual crimes. You've just learned the basic code. So the only question left is, what other mysteries are out there waiting for you to solve?